The purpose of this video is to give an overview of root loci. So, what are root loci and why are they important? And how do I compute them? Well, the first thing to recognise is what the words mean. So a locus is a path, or loci are paths, the plural. So root loci are the paths followed by the roots of the closed loop pole polynomial as the open loop gain changes. So why do the closed loop poles change? You see here I've taken a simple feedback loop with a compensator M and a system G. And you'll also notice that within the compensator I've included this scalar parameter k, which is what we're going to change when we talk about root loci. Calculating the closed loop poles, what do you notice? The closed loop poles depend on this parameter k, so this polynomial is going to change if you change k. So what are root loci and why are they important? Basically, they're how the roots of p change as I change k. We'll give a simple example and then it will become more apparent. So here's the example. I've got a simple system G and my compensator M is just going to be a scalar gain k. And I'm going to take a number of specific values, and what I'm going to do is just calculate the closed loop poles for a number of different values of k and then plot them on an Argand diagram. So first, what's the closed loop pole polynomial? There it is, s squared plus 4s plus k. And then you can see for different values of k, what do you notice? I get a different closed loop pole polynomial. So there I've just listed them again, and what I want to do is find the roots and sketch them in an Argand diagram. So there we are, I've found the roots for you. Put it in full, I'm not dwelling on it because these are simple computations. So the next thing is to sketch them. Well, here we go. K equals 0, I get s plus 4 and s plus 0. So that gives me a pole there and a pole there. And I'll change colours. K equals 1 and I get poles there. So you can see I get a pole here and a pole here. And we'll go to black. I'm afraid I've only got 3 colours. K equals 4. We go to s plus 2 and s plus 2. So you see we have 2 poles at that point there. And I'll go back to blue again. And then k equals 10. I've now got some complex poles, and you'll see we have poles there and poles there. And finally, k equals 50. The poles are going to have a larger imaginary part. So it's clear that as I change gain, the poles change, but it's also clear that there's a pattern to this. So what you should see is the poles move. They start from where they were and then they move until we end up, oops, don't know what happened there. They move and they join at this point here. And then, having joined, oops, don't know what, it's not very happy. Having joined, they then get a larger and larger imaginary part. And these paths in these large green arrows are called root loci, the paths the closed loop poles follow as I change k. Now, what do we want to do? We want to know where are the best closed loop poles. So in terms of these paths, I need to ask myself, which value of k am I going to choose and why? So here's an example. I've just taken 2 of those values of k equals 4 and k equals 10, so I can have both poles here, or I can have a pole here and a pole here. Now, which of these do you prefer and why? But the key thing is the root loci is showing you what your options are. Now, for these, you can see they have the same real part, so they've got the same decay rate, but they've got different damping and transients. And hopefully that's roughly apparent here. You can see the blue curve corresponds to k equals 4, slightly slower rise time, but less overshoot and oscillation. And with k equals 10, faster rise time, but a bit of overshoot. You have to make the choice. What is it you want and why? Now, a homework task. Choose another system. I've given it an example system here, but you can choose some of your own choice and go through the same process. Find the closed loop poles for a number of different values of k, plot them in an Argand diagram and see what the patterns are. Now, doing this by hand is rather tedious. So, why don't we use a computer to do it? Because once you understand what you're doing, There's no need to do the tedious computations by hand anymore. Let the computer do the hard work. So here's an example of the R-locus tool. I'll highlight that down here. So this is the R-locus tool in MATLAB, and you can see the command I've used in MATLAB down there. So I've put in a transfer function object G, and I've just typed R-locus brackets G, and it comes up with the plot. And what you can see is it's given me the values here for k equals 0, those starting values, and then it's shown you the loci. So basically you have to infer from this as k increases, these come together and then they go up. So that's the same example that we've already done. But obviously this isn't showing the values of k, it's just showing the loci. What if you want the values for k? Well, what you can do is you can use a slightly different command. So you can see here I've put in R-locus G, and then I've put in 4 different values for k. It didn't have to be 4, you could have put 10, 20, 100 as you please, and it will then output the corresponding closed loop poles associated to those different k. So you can see the R that's come out, and so for example the third column corresponds to the third value of R. So those are the closed loop poles for k equals 4, and the second column for k equals 1, and the fourth column for k equals 10, and so on. Now there is another method you can use in MATLAB, and that's CISO tool, and this window is a bit more interactive. It allows you to change k and see the closed loop poles move, and then you can visually set the closed loop poles where you want them to be. So I'll show you this very quickly so that you can see. So here's CISO tool with a particular system G, and you can see the root loci is this plot for me over in the top right hand corner. Now the key thing is it's showing the closed loop poles with these pink blobs. So the pink blobs are where are the current closed loop poles. Now if I go edit compensator and get the compensator window out, so you can see with a compensator gain of 1, the closed loop poles will be on those pink blobs. What happens if I change that k value to 0.1? You will see those pink blobs move. The closed loop poles are in a different position. So I can actually get different values for closed loop poles by changing k. I can try 0.5 and you'll see they move. Or I can try 2 and you can see they move. So basically, as I change the gain, the closed loop poles change, and you'll see CISO tool is also showing what's the corresponding closed loop step response down here. Now I can, if I want, actually pick up those closed loop poles with this hand and drag them. Say, I don't really want the poles in the right half plane, that's not very wise, but I can drag them and I can say, actually, I quite like them to be roughly on that intercept point. See where I've put them? And if I'm saying, oh, but what's the corresponding value of k? CISO tool's calculated it for me. There it is, 0.23 will give me the closed loop poles in those positions. So that was a very quick whistle-stop tour of CISO tool. So a homework task for you is to play around with these tools and just get familiar with, can I calculate the root loci with these different tools, and am I comfortable? Now, to finish off this quick introductory video, performance specifications. We need to ask ourselves which value of k is best, and we can only do that if we have a clear set of aims and objectives or design requirements. Now it's normal for these requirements to be specified using terms which are analogous to behaviours of first and second order systems. So we'll give some examples. You might ask for the settling time or the time constant, in essence the slowest pole. The maximum allowed overshoot, which in essence is a damping ratio criteria. The rise time or the bandwidth, which is to some extent similar to the settling time. Offsets to steps and ramps. So these are the sorts of criteria that you might want to use in deciding where is the best value for k. Now, this is the type of diagram we've done in the earlier videos, and it enables you to actually make some objective decisions. Which poles are best? So if I put a typical root loci down here, say the one we did before with 0 and 4, so there's the starting values. The root loci came together like this and then went off like this. So in terms of values for k, where would you want to be on this root loci? And you're going to say, well, probably I'd want to be somewhere in that region there. because it means my slowest pole is as fast as it can be. So you're not so small k that you've got a really slow mode, but I don't want k to be too big because then I'm oscillatory. So you can see how the root-loci plot overlaps with our understanding of what are good pole positions with this sort of figure that I've shown you here. Offset, it's important to be clear on how you calculate offset. So just for completeness, I've given the formula here, but you can look at that offline because we've done it elsewhere. And you'll often find in control design, people also look at the offset to ramps. So the formula offset to ramps is given here, or you may see this ramp error constant term here. So some conclusions. We've introduced the concept of root-loci for observing the impact of changing compensator gain on the closed-loop poles and behaviour. You can compute the poles for different choices of gain by hand and plot them, but this is tedious, so you only want to do that enough to gain understanding. Once you understand, it's easier to use computer tools to provide a plot over a wide range of gains, and from that plot, you can now choose suitable values. But obviously, to do that, you have to be clear on performance criteria. And finally, to finish, I would recommend you use tools like MATLAB, RLocus and CISO tool because they really will facilitate the design process because they cut out all of the tedious number crunching.